of Chemistry, University of St. Jamshoro. Today we are going to start with the mass spectrometry. It's an analytical method to measure the molecular weight of the samples. It is the most accurate method for determining the molecular mass of the compounds and its elemental composition. In a simpler terms, a mass spectrum measures the masses within a sample. Mass spectrometry nowadays is the most important and reliable source to get the structure of any molecule, and most of the biological studies is also conducted via mass spectrometry. In this technique, molecules are bombarded with a beam of energetic electrons. The molecules are ionized, transformed into electrically charged particles, and are broken up into many fragments, some of which are positive ions. Each kind of ion has a particular ratio of mass to charge, that is m/z ratio. For most ions, the charge is 1, and thus m/z ratio is simply the molecular mass of the ion. Nowadays, most of the biological studies is conducted via mass spectrometry. For example, if we take two different compounds, that is amino acids, both will be differentiated by their masses. For example, glycine has a molecular mass of 80, whereas alanine has 94. Second thing that is coming up is the charge, that if it is plus positive, single positive, or double positive. Now, if we split a glycine molecule into slices or break it from different regions, like the slicing parts are also checked for the mass and check for the charge respectively. In mass spec, we take mass to charge ratio of different segment of the molecule to find their identity. We can also separate two isotopes, that is carbon-12, carbon-14, and oxygen-16, oxygen-18 with the help of mass spec. This is glycine. Its molecular weight is 80. Now, if you break these two parts, if it slice it down into two parts, these parts will be checked for the mass and they will be checked for the charge ratio. This is the alanine molecule. Now we'll discuss the mass spectrometer apparatus or mass spec apparatus. Inside the mass spec, there are three regions, that is sampling, electrical field, and detector. Now what is happening inside the apparatus? Suppose we have an original molecule M and is attacked by an electron or a high-speed electrons, and on hitting the molecule, get one electron out of the molecule and is left with only one electron and becomes an ion, that is M plus with an electron. So a molecular ion or parent ion or a radical cation, as the magnetic force only affects the charged particles, so that was the point of making it a cation, which is very unstable, as molecules tend to stay in the stable most form, that is having two electrons that can form a covalent bond. So we'll try to be stable again and will start to break themselves apart into smaller fragments which are stable. So the molecular ion break into smaller ions and are called fragmentations, which are more stable than the molecular ion. The molecular ion will now go into the detection apparatus, and there it will be detected. The apparatus uses a magnetic field to detect the properties, as magnetic force only affects the charged particles. The apparatus can use adjustments to magnetic field to determine the m/z ratio, where m stands for mass and z for charge. M/z equals to mass by charge. So now what is z? For this molecular ion, M plus, it is 1, as it has only one positive charge. So m/z is just going to tell us the mass, which is m/z equals to m over 1, that is z equals to 1 equals to mass. And it turns out that almost all particles and fragments that we are going to run through the apparatus will have a charge of 1, single plus equals to 1, or plus plus equals to 2, because it's a methane molecule. And show how many of the molecular ions are getting to the detector in figure 1, and we can see the horizontal axis to see what the total mass is here in the graph. So for example, if original molecule was methane, the molecular ion or is the radical cation of methane, so m/z equals to 12 plus 4 equals to 16. So molecular ion equals to methane. So you get a mass here 16 as shown in the graph. Here in figure number 2, you can see the molecular ion peak is less taller as compared to the base peak, right? So that is the base peak. It is one of the fragmentation peaks, but it is the tallest peak, and it is next to the molecular ion peak. So, if we talk about the relative heights of the two peaks, that is the base peak and the molecular ion peak in figure 1, we can see that greater height of molecular ion peak as compared to the base peak refers to that more of the molecular ions reach the detector than the fragments. Now here again there is a figure. You can see here molecular ion peak of methane CH4. The tallest vertical peak is of molecular ion peak. For methane, the parent ion is the most abundant. Now you can here simply see I've written here molecular ion peak is the parent peak, and it's always farthest to the right as it is the heaviest of all the fragments, and this is the case of methane. Whereas the next peak, as it goes on the left side, you can see the molecular weight decreased from 16 to 14, and the methane molecule, it turns into methylene, that is CH2, and with a mass of 14, right? So this is something very interesting. So for methane, the parent ion is the most abundant. So that peak is the molecular or the parent ion peak, which is also farthest to the right, and the tall vertical peak is the base peak. But now the point is whether the molecular peak may or may not be the base peak. This is a question. So sometimes it is and sometimes it isn't. As conceptually, these are two different things, but remember, in case of methane, the molecular ion peak was the base peak, but here in this figure 4, the molecular peak is not the base peak. So base peak is the vertically tallest. So what info mass spectrometry give us? The mass spec tells us the molecular weight of the original parent ion. We can get the molecular weight of the compounds because the molecular weight is just given by mass to charge ratio. That is M by Z ratio of the parent ion. Remember, the charge is always 1. The horizontal axis just tells us the mark. Now, how atoms are ionized? Atoms and molecules can be deflected by magnetic fields. Now, here in the magnetic field, in the instrument, there's a magnetic field where the atoms, that is, or you can say the ions, they are deflected according to their mass and their, you can say, weight. Provided that the atom or molecule must be converted to an ion, definitely they are supposed to be converted into an ion before they enters into the magnetic field. Otherwise, they will not be detectable, as I just mentioned earlier. So electrically charged particles are affected by the magnetic field, although electrically neutral ones aren't. This is now the concept is clear. That was the main idea of making them a cation, right? So the molecules or atoms are ionized by knocking one or more electrons off to give a positive ion. Now let's come to another topic, that is isotopes, because I just told you that isotopes are also detected by a mass spectrometer. So isotopes and mass spectrometer. Now here you'll learn about an isotope and you'll be able to describe the key points of mass spectrometer, and finally we'll learn to analyze a mass spectrometer. We know how to use an atomic number and mass number to work out the number of protons and neutrons and electrons and ions. Now here this is lithium. You can see an atomic number in the figure, number Z, and it has protons, 3 protons, whereas total number of protons and neutrons added together is the mass number A is 7. Now one thing you have noticed that mass number in periodic table is in decimals. So mass number for lithium is not 7 but actually 6.9, and that is due to the presence of isotopes. Isotopes are atoms of the same element with different numbers of neutrons and different masses. This is the key definition of isotopes. How much, you can say, tells us how common each isotope is. Around 69% of the copper atoms are for left side isotope, whereas 31% of copper atoms for the right one isotope. So the question is, how do we actually work out the mass number and abundance for isotopes? To do this, we use a machine called mass spectrometer. Now let's come to the time of flight mass spectrometer, which is also called TOF MS mass spectrometer. This is called time of flight mass spectrometer. You can see here it has got a sample chamber where a sample is put, and then there is a drift chamber where something happens. Now let's read out. This is called the time of flight mass spectrometer. In the first stage, we take a sample of the element that we are about to analyze. This contains all of the different isotopes for that element. We place this in the sample chamber. This then passes through the process called electrospray ionization. So now let's see what is that supposed to mean. Now here, the TOF MS, how does it works? This is something very important to note. Now here the sample is injected and it should be a gas phase, in a gas phase or in a liquid phase, or it can't be a solid. When it enters the main cavity, there's a heat here, right? So if our sample is in liquid, it needs to be vaporized. So second stage is vaporization. The next stage is ionization by a high voltage electricity called ESI, electrospray ionization. Here atoms are ionized, that is, electron is knocked off the atom to form a positively charged ion for acceleration further caused by negatively charged set of plates within the you can say a small group between them, small gap between them. And this negatively charged plates will attract the positive ion straight through the middle of them, forcing them to the next chamber called ion drift chamber, which is shown in the figure, and is the main basis of TOF. Now, different sizes of ions with different colors, that is, you can say different sizes like heavier, medium, and light masses will you can say will be measured for, and you can say the TOF will measure for how long these ions will take to fly through mass spectrometer heading towards TOF. They have a constant speed. This is a very important point to remember. These ions, they with the different sizes, they have a constant speed and have same amount of kinetic energy. Some will be lighter. Some of them will be lighter ones, will be more quicker as compared to the ones that are heavier and hit the detector and is just you can say reach the electronic plate where electric current is produced, and then it is sent to the computer, which produced a spectrum which we see it. So this time of flight spectrometer, it converts all the atoms of the element to positive ions. As I just told you, the positive ion then passes to an electric field. This is the diagram where you can simply say how this electron spray ionization produces positive ions of the element. So the positive ion then passes to an electrical field. This causes ions to accelerate, giving them kinetic energy. When ions pass through the electric field, they all have the same kinetic energy, which I just mentioned here. The ions now drift on the chamber with the different speed. Lighter ions will move faster, which I just told you, than the heavier ones. When the ions reach the end of the chamber, they are detected. Now here you can simply see a rough diagram where time of flight, I have shown how there are the sample to be injected and then it is vaporized here, heat is supplied here, and then it accelerates towards these plates, the set of two plates. And from these plates, they will pass into the ion drift chamber where they are going to be, detected according to their different masses, that is different sizes they have. The lighter ones will move faster and reach the detector as compared to the heavier ones. So this is the same text written on the left side. Lighter ions will move faster than the heavier ions. When the ions reach the end of the chamber, they are detected. The time it takes from ion to make its way down the drift chamber is used by the machine record the mass of the ion, and machine also tells us the percent abundance of each isotope. So now here we are going to learn or read a spectrum, how to interpret a mass spectrum. Now this is a copper spectrum. Here you can see the masses and the relative abundance on the vertical side, and you can say the masses M by Z ratio given here. We'll learn the mass spec of element copper. The spectrum has got two peaks telling us that copper has two main isotopes. The y-axis shows the relative abundance for the isotopes. Usually these abundances have been given on top of each peaks. You can see 69 and 31. These are being mentioned over here. Whereas on the x-axis, we have got the M/Z ratio. This is the ratio of the mass of each ion to its charge. As remember, in start of analyzing, we generated positive ions. We can get ions with single positive charge or double positive charge, as I just mentioned before, or even greater. The mass spectrometer compensates for this by giving the M/Z mass to charge ratio. Now, from this, we get that this is the mass of each isotope. Here you can see it is clearly showing it. So the 3 peaks means 3 isotopes, whereas masses and abundances would be 24, 79%, 25, 10%, 26, 11%. So now we have learned to interpret a mass spec of isotopes. Mass spectrometry needs. What does it need? Yes, it needs ionization, number 1. For example, we can take the example of a protein and a peptide. If it is injected into the MS machine, mostly these are the macromolecules that are, analyzed. Then, of course, the separation according to mass and charge ratios. Then activation, that is proteins are broken into smaller fragments, that is peptides. Then mass determination according to mass to charge ratios are determined for the ionized protein fragment peptides. Mass spectra is used in 2 general ways: to prove the identity of the 2 compounds, to establish the structure of a new compound. The mass spectrum of the compound helps to establish the structure of a new compound in several different ways. It can give the exact molecular mass, it can give a molecular formula, or it can reveal the presence of a certain structure units in a molecule. This is a diagram of a typical mass spectrometer. Here you can see a probe from where the sample has been ejected, then the ion source, then of course the beam of electrons that are passing through, then there's an insulator, and there are slits from where these electrons are being passed through. Ion beam is shot onto them. Then there is a magnetic field in which you can see there are 3 different types of ions. Ions that are too light bend too much, whereas the ions that are too heavy bend too little. Only ions of the right mass can enter the detector, and this is called the flight tube, right? This is the flight tube. That is why it is called TOF, right? TOF, time of flight. So this is a flight tube. So now here only ions of the right mass can enter the detector. There's a detector slits are there, and finally it will reach the detector, and we can see, and there is a vacuum pump also attached to it. So, and finally it will reach to the recorder where we'll be able to see the different peaks and the fragments.